Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to discuss our next thermodynamic quantity, which is going to be the Gibbs Free Energy. And so the Gibbs Free Energy is, it can be abbreviated as capital G. And what the Gibbs Free Energy does, it gives us a quantitative perspective to evaluate whether or not a chemical reaction is going to be spontaneous or non-spontaneous in the forward or reverse direction. And so here I've kind of drawn this like roller coaster looking cart at the very peak of this hill. And so if this cart were to move in the forward direction, then it would be spontaneous in the forward direction and it would be non-spontaneous in the reverse. And the same thought process works if you guys think about it in reverse. And so for example, if this cart goes backwards, then it's spontaneous in the reverse direction and non-spontaneous in the forward direction. And so this idea of Gibbs free energy is going to be derived, and we'll see this in just a bit, by incorporating other thermodynamic quantities such as enthalpy and entropy, which are topics that we've discussed in prior lecture videos. In addition, we're also going to incorporate temperature, and we're going to see how these three state functions, enthalpy, entropy, and temperature, produce this concept of this Gibbs free energy, which allows us to predict if a reaction is spontaneous or non-spontaneous in the forward or reverse direction. To do so, we need to understand where the idea or where Gibbs free energy comes from. So to make the link between enthalpy, entropy, temperature, and Gibbs free energy, we need to first discuss the second law of thermodynamics. And so according to the second law of thermodynamics, it states that when a spontaneous event occurs, right, the total entropy of the universe increases. And so let's go ahead and talk about this term universe. So this word universe can be taken literally or it can be taken figuratively. Since the course that, since this is a chemistry course, we're not taking this word literally. We're not talking about the whole universe here. That involves the planets, galaxies, stars, etc. However, the universe that we're looking at is simply a chemical reaction, right? And so the system that we're always studying is a chemical reaction for chemistry. And the surrounding is just what the immediate surrounding is around that chemical reaction. And so the combination of these two describes the universe for that chemical reaction, for that subject. Now, we can go ahead and summarize the second law of thermodynamics as simply the total entropy is going to be greater than zero because the total entropy of the universe is increasing. And so the only way that value translates mathematically is that if it's greater than zero. We can go ahead and decompose this change in entropy total to its parts. And so the total entropy consists of the sum of the system and its surrounding. And so here we can expand this definition of the change in total entropy to the change in entropy of the system plus the change in entropy of the surroundings. Now, I want you guys to notice that we're using this delta sign, which reflects a change. And so by using this delta sign, we're talking about a thermodynamic process, which makes sense because when we're performing a chemical reaction, we're going from one equilibrium state to another equilibrium state. We're going from reactants to products. Okay. All right, and so what we're going to do is we're going to combine both of these equations to create one specific statement. And then we're going to go ahead and make some assumptions and some derivations, if you will, to understand how this idea of the Gibbs free energy comes up. And so when you guys combine both these two statements, we get the total entropy of the universe is equal to the sum of the entropy of the system and that of its surroundings. And we know that it's going to be greater than 0 because according to the second law of thermodynamics, where the total entropy is going to increase. And so what we're going to do is we're going to manipulate this equation so that we can get a relationship between enthalpy, temperature, and entropy of the system. This will allow us to define this idea of the Gibbs free energy. So the first thing that we're going to do is we're going to look at the units for entropy. And if you guys go back previous lecture, when we wanted to determine the change in entropy, remember that the unit moles gets canceled out when we multiply it by the coefficient of a balanced chemical equation. And so we simply have joules per Kelvin as the final unit for the change in entropy. And so Kelvin is a unit for temperature, and joules is a unit of energy. And since we're talking about thermodynamics here, we're simply talking about heat as a form of energy. And so we can go ahead and replace this term, the change in the entropy of the surroundings, to reflect the heat of the surroundings divided by temperature. And so this expression here is simply the unit that describes entropy of the surrounding, or just entropy, change in entropy just in general. Now, if you guys recall, the heat of the surrounding is also a part, how do I say this? And so if you recall from thermochemistry, if a substance loses heat, another substance must gain that heat. And so Q of surroundings is not like a standalone concept. It's related to something else. And so here, I went ahead and wrote it down for you. Imagine a combustion reaction, right? Or lighting a match. That's an example of a combustion reaction. The substance, the combustible substance, which is this hydrocarbon, when the combustion reaction occurs, that substance is going to release heat. So the system is losing heat. Now that heat needs to go somewhere, so the surrounding gains that heat. And since they're proportional or equal to each other, what we're going to do is we're going to replace this term with that of the system. And in doing so, we get this expression. So the really cool thing about this is the fact that if you guys are looking at the description, we're now specifically talking about the system. We're no longer talking about the surrounding and then the system. We're just specifically talking about the entropy of the system minus the heat of the system. And so if you guys recall, the heat of the system can be defined by one of these thermodynamic quantities if the heat of the system was measured at a specific condition. And so if we are measuring the heat that the system lost at constant pressure, what thermodynamic quantity do we get? We get enthalpy. And so the heat of the system, if it's measured under constant pressure, it will give us the enthalpy of the system, or the change in enthalpy of the system. And so the last thing that we're going to do is we're going to multiply negative t on both sides of the equation. So we're going to kind of manipulate this chemical equation. We're going to see what happens. And so if I were to multiply both sides of this equation by negative t, that's going to give me, so I'm going to distribute this negative t to this term, negative t to this term. That's going to give me negative t delta S, which is the entropy of my system, plus T times this by delta H, or the enthalpy of my system. Divide this by T. And when you multiply negative T on the side of the inequality, this inequality is going to flip. Okay? And so we're going to flip that inequality, and anything times 0 is just 0. And so what we get is this expression where the t's will cancel out, and what we'll get is minus t delta S of the system plus delta H of the system. Another way for me to represent this is just me flipping some terms around. So since this guy is positive, maybe I can kind of flip it around this way. And I'll erase that. So it's negative, so I'm carrying that negative. Okay. All right. So what I just did is I just moved the terms around so that my positive value is seen first and my negative value is seen second. And so this is telling us that for a spontaneous reaction to occur, the enthalpy of the system minus the temperature times that by the entropy of the system must be less than 0. Okay? And so this is this is the definition that we're going to apply to for the Gibbs free energy. Okay? So this second law of thermodynamics is really, really powerful because it's giving us the relationship between enthalpy, it's giving us a relationship between enthalpy, temperature, and entropy. And all of these terms, all of these state functions put together, if they're less than 0, then we've now been able, we will be able to determine why reactions are spontaneous or non-spontaneous in the forward or reverse direction. And we'll be able to predict it as well. And so now that we've gone through that derivation, let's go ahead and talk about Gibbs free energy. So the Gibbs free energy is another thermodynamic quantity that includes all three factors that affect the spontaneity of a chemical reaction. In this case, the three factors are temperature, entropy, and enthalpy, okay, as seen here in our derivation. And so because enthalpy, entropy, and temperature are state functions, Gibbs free energy is also a state function. And so what that means is we can treat it as a descriptor that will describe the thermodynamic process as we go from one initial equilibrium state to another equilibrium state, which we assume to be the final equilibrium state. And so one way that you guys can think of Gibbs free energy is like that residual energy that's going to be released from spontaneous reactions. And it's going to be like once the interplay between temperature, enthalpy, and entropy, all of that stuff is put together, the residual energy is the excess energy that's being produced is going to be the Gibbs free energy. And so it's really important for us to understand that this residual energy comes from the interplay among temperature, enthalpy, and entropy. And so at constant pressure and temperature, we can go ahead and describe the thermodynamic process. We can go ahead and say that the change in Gibbs free energy, that's the delta G, is equal to the change in enthalpy minus T delta S. And so this statement right here comes from this statement that we derived at the very earlier on in this lecture. Okay. And so this is telling us that this enthalpy is, so the Gibbs free energy of the system is equal to the change in enthalpy of the system minus the temperature, which is more of like a surrounding type of thing, times that by the change in entropy of the system. And so once again, the system is the subject that we're studying, which in this case are chemical reactions. And so if we are able to measure the enthalpy and entropy of the chemical reaction and record the temperature that they were performed, we can go ahead and predict whether or not the reaction is spontaneous by looking at the value of the change in Gibbs free energy. Okay. So let's go ahead and talk about that. What would happen if the Gibbs free energy is less than 0, equal to 0, or greater than 0? And so if you were to perform like all these calculations in lab or on an exam or on a homework or worksheet, what does the sign of the change in Gibbs free energy tell us? And so if you guys recall, for a spontaneous event to occur, all of this must be less than 0. Okay? And so if the change in Gibbs free energy is less than 0, then this is telling us that the reaction is going to be spontaneous. Now, if it's it doesn't tell us if the forward or reverse reaction is spontaneous. That comes from the perspective of the problem or what you're doing. It's just simply telling us that, if you calculated the enthalpy, the change in enthalpy, and the change in entropy in the forward direction, then the change in Gibbs free energy is referring to the forward direction. But if your calculation for enthalpy and change in entropy is for the reverse direction, then the change in Gibbs free energy would also reflect that for the reverse. And so once again, it's important for us to understand that the change in Gibbs free energy only tells us if it's spontaneous or non-spontaneous. The direction is dependent on the perspective. All right, so when delta G is equal to 0, that's when our system is going to be at this equilibrium. And we'll talk about this idea of being at equilibrium a lot more in a future lecture video. Next, or last but not least, so here if the change in Gibbs free energy is greater than 0, in other words, its positive value, then that reaction is going to be non-spontaneous. Once again, the perspective of it being non-spontaneous depends on the direction, depends on the perspective. Okay? And so to make sure that we have a better understanding, I'll write it here. So spontaneous means delta G is negative. Equilibrium, that means that delta G is equal to 0. And for non-spontaneous, delta G is going to be a positive value. Okay. Cool. So the next thing that we're going to do is visualize this. And this is known as the Gibbs Free Energy diagram. So the Gibbs Free Energy diagram is going to be very similar to the potential energy diagram that we talked about in kinetics. And so very similar to the potential energy diagram, the Gibbs Free Energy diagram is taking a look at the progress of a chemical reaction with respect to the change in Gibbs free energy. Hence, the y-axis is representative of that of the Gibbs free energy, and the x-axis is representing the course of the reaction. And so, since the reaction perspective, looking at the arrow that I drew, is from left to right, we're going to assume that this is our reactants, and that these are our products. And so we can talk about, the activation energy, all that stuff still applies. But in this case, we're just going to simply look at the outcome. And so if you guys recall this dotted line, I'll go ahead and change so this area right here, that's going to represent our reference point or 0 point with respect to the free energy of the reactants. And so as we're, investing energy, so to speak, where the change in Gibbs free energy is going to increase. Notice that it's more positive, right? So if we're increasing our Gibbs free energy, that means that this is a non-spontaneous reaction. So we have to have some energy investment. Okay, and that makes sense. For anything good to come, you have to invest energy, right? For you to get an A in the class, you have to study, right? So that's your investment of energy. Now, at some point in time, you guys are going to be so good in chemistry where you guys are going to just ace all of these exams. And so that's going to be this downward slope, if you will. So here you have this energy release, let's just leave it like that. So we have this release of free energy. And when you hit this point, when the graph hits that dotted line, you're technically at the 0 point. And so that would be like an equilibrium, right? And so this point would probably represent the equilibrium for the reaction. Now notice that the Gibbs free energy is going down even more. So this is a negative slope. And as we're going down even more, then this quote unquote 0 point, which references the starting free energy of the reactants, this is telling us that the reaction is going to release more energy than it took in. And so from the dotted line to the free energy of the products, that's going to represent this idea of a negative value for delta G. And so if delta G is negative, because it's below that 0 point, it's a relative 0, by the way, Anything below that relative zero is going to be a negative value. So this is going to tell us that spontaneous reaction is occurring. And in the course of this spontaneous reaction, it's releasing, this excess, this residual energy. And overall, we are going to label this graph when we get a spontaneous reaction as exergonic. And so exergonic reactions are typically spontaneous. Well, not typically spontaneous, they are spontaneous. The reason why is because the value for delta G is negative. So this is an example of an exergonic reaction. Please don't confuse this with exothermic. Okay, so there's a G in gonic, so we're talking about free energy or Gibbs free energy, and that's one way you guys can remember this. When you guys are thinking about, your potential energy diagram, so this is PE, potential energy. This is what we covered in, what's happening? So this is what we covered in kinetics. When you guys have a graph that looks like this, since it's respect to potential energy, this is delta H, okay, and it's enthalpy. And so for enthalpy, this is going to be exothermic. So please be very careful with these two concepts. The graphs and the sign looks very similar, but enthalpy alone cannot solely predict if a reaction is both, it cannot predict exclusively whether or not a reaction is spontaneous or non-spontaneous. Enthalpy just tells us that there's going to be a net release of energy. Now, whether or not that net release of energy is in the form of free energy, we don't know, right? We have to take in consideration temperature and entropy. But when you're talking about Gibbs free energy, if you guys have negative delta G, then that is the residual energy that is released after taking consideration all the other factors that affect spontaneity, which is enthalpy, entropy, and temperature. Right? So let's go ahead and look at the reverse. So once again, we've seen a very similar graph when we were talking about potential energy diagrams and kinetics, but once again, that's with respect to enthalpy. Here, if you look at the y-axis, notice that it is Gibbs free energy. And so the brown line that I drew, the brown dotted line that I drew, is representing that relative 0 point. And that relative 0 point gives us, this reference point that we're working with. And it's typically going to represent that of the reactants. Okay? So we're referencing the 0 point from the reactants to that of the products. And so here in this case, once again, if you guys are looking at following this graph, notice that we're going up. And so if we're going up, that means we're increasing delta G. If we're increasing delta G, that process would probably be non-spontaneous. And then all of a sudden, we get this drop. So some part of it becomes spontaneous-ish. But, if you look at the sum of this non-spontaneous and spontaneous section, overall, we get a value that's for the products that's much higher than the reactants. And so if we were to extrapolate, and maybe I'll do this in a different color. So here, notice that the free energy for the products is much higher than the free energy of the reactants. And since we have a net increase of delta G, then this is telling us that overall the reaction is non-spontaneous. Okay, so the condition is, the products, the free energy of the products is much greater than the free energy of the reactants, which is similar to what we discussed in kinetics. And so, same thing here. Notice that the 0 point, if I extrapolate this dotted line, this is going to be the free energy of the reactants. And if I kind of trace this line back as well as I can, then this is roughly the free energy of the products. And so you can see that in this scenario, the free energy of the products is less than the free energy of the reactants. Okay. Or you can look at it in reverse. The free energy of the reactants is greater than the free energy of the products. Either way, it's going to lead you to the same conclusion, that it'll be an exergonic reaction. And the value is negative delta G. Okay. And so what do we name this, right? What do we name this phenomenon? In the previous graph, it was called exergonic. And if we're doing this for non-spontaneous reaction, we can't say endothermic, but we can go ahead and replace that thermic with gonic. So this is going to be endergonic. And so endergonic reactions are always non-spontaneous, such that the free energy of the products is always greater than the free energy that it began with. All right. So now that we've kind of created this visual for both, exergonic and endergonic reactions, for both spontaneous and non-spontaneous reactions, the last thing that we're going to do is we're going to learn how to use this equation, so to speak, to qualitatively assess the spontaneity of a chemical reaction. Okay, and I'm going to go ahead and zoom out just a little bit. So here we are going to consider six scenarios, really. And so right now it's a 4 square, and you'll see why I said 6 in just a second. And so remember that for a spontaneous reaction to occur, delta G must be negative. And so based on the signs of enthalpy and entropy, could we predict whether or not a reaction is spontaneous or non-spontaneous without having to perform the math? Is there some way that we can just look at the signs and think about it very critically to determine whether or not delta G is going to be negative or positive? Okay. So let's go ahead and start, just to demonstrate what I'm getting at. So we're going to go ahead and look at this first box on the top left. So I've kind of created this 4 square, if you will. And so in the very top here, we have our first condition. We have, delta H, or enthalpy, being negative, right? And so if our enthalpy value is negative, and if our entropy value is positive, what would the sign be of delta G? And so I'll go ahead and write that down here. So delta G, maybe I'll zoom in, is equal to delta H minus T delta S. And so if this is negative, and if entropy is positive, that means that this change in entropy is positive. T will always be negative. Okay, oops. And so if we multiply these two together, negative times positive is, well, negative. And so I guess just to lessen the confusion, let me add one more item. Okay. I'm going to go ahead and just put this invisible plus, right? Just to kind of separate these terms out. And so there's a plus there, there's that plus there. Okay. And so technically I didn't really change anything, right? Positive times a negative is still a negative. And so I'm just separating out the terms to lessen the confusion in what I'm about to do. And so here, since temperature always has that negative sign in front of it, it's going to be negative. I'll use this. And so in this scenario, entropy is positive, so this is positive. And so when you multiply both these together, you guys get a negative value. So all I'm going to do is bring down this negative, and I'm going to ask myself, what's negative plus negative? Well, a negative number plus a negative number, if you're in debt, you're even in more debt if you add more debt to it. And so overall, it's going to be negative. So what this is telling us is that if your enthalpy value is negative and your entropy value is positive, you will always get a negative value for delta G. And so here we can say that the combination of the signs for enthalpy and entropy will tell us that it's going to be spontaneous at all temperature. Okay. So hopefully that made sense. So let's go ahead and look at the opposite side, right? I'm going to zoom out here just so we can see what the parameters are. So what would happen if our enthalpy is positive and our entropy is negative? And so once again, we're going to go ahead and write our chemical equation, or I'm sorry, not chemical equation, just an equation. So here we have delta G is equal to delta H minus T delta S. I'll do this in blue. And so here we're looking at a positive delta H, so I'll go ahead and do that. So positive delta H. And once again, I'm going to separate this out. Maybe I'll do this in, I don't know, pink. Right? So that plus sign just separates out the enthalpy value from minus T delta S. And so I know that my temperature is always going to be negative, and I'm multiplying it by delta S. And so according to this parameter, our delta S is negative. And so if you multiply a negative and a negative, what do we get? We get a positive value. And so I'm going to bring down this positive and then change my color to pink. Okay. So what is positive plus positive? Well, it's a positive value. And so this is telling us that at all temperatures, when you have a combination such that enthalpy is positive and entropy is negative, then our Gibbs free energy will be a positive value. So therefore, we can conclude that this will give us a non-spontaneous reaction at all temperatures. Okay. All right. So let's go ahead and do this next one. Hopefully you guys are understanding what I'm doing here. So here I have delta G is equal to delta H. And I'll just go ahead and put that positive sign in pink just to be consistent. So that positive sign is just merely there to separate out the T delta S term. Okay. And so once again, here we have a positive value as indicated by my condition. So enthalpy is positive. And so if I look on the left-hand side, notice that entropy is positive. And so this term will be positive. We know that this term will always be negative. And so what happens when you multiply a positive with a negative value? You get a negative value. Okay. And if you guys get a negative value, and you're adding that to a positive value, one might say that they cancel out, right? But it doesn't cancel out, right? The reason why it doesn't cancel out is because we don't have actual values. We can't assume that all these values are equal. What this is telling us, though, is that if we have conflicting signs, then the Gibbs free energy is not spontaneous at all temperatures. So we have conflicting signs or conflicting results. One is positive, one is negative. And so therefore, we can conclude that delta G is not spontaneous at all temperatures. This implies that there might be some type of temperature range in which it could be spontaneous. And so let's think about this some more. If I wanted my reaction to be spontaneous, that means I want delta G to be negative. And for my delta G to be negative, the negative term must be much, much, much higher than the positive term. And the only way that can happen is if we're going to trace back, right? So this negative came from this negative, which came from this negative. And so since ultimately it is temperature that is producing this negative value, then that means that if I wanted a spontaneous reaction, this term must be far, far greater such that the sum of these two will produce a negative value. So long story short, our reaction will only be spontaneous at high temperatures. Okay? And at high temperatures, a high temperature value, it's going to give us a negative result for delta G. So here we're going to say that um, delta G is only spontaneous at high, oops, what happened there? Temperatures. Okay, so hopefully you guys understand that. And so obviously, if your temperature is not very high to the point where that negative sign does not dominate the equation, then your enthalpy value, which will be positive in sign, will dominate. And therefore, at low temperatures, the delta G is non-spontaneous because the value of delta G is going to be positive at low temperatures. All right, so let's go ahead and look at this last table right here. So the condition is that we have negative delta H, negative delta S. So once again here we have delta G is equal to delta H. I'll leave a little space here, minus T times this by delta S. And then I'll go ahead and put in that pink positive sign, that plus sign just to separate those two terms. And maybe I'll just put like plus and plus, who knows. All right, so in this case, we have a negative value for delta S. So let's go ahead and say, I'm going to replace this term with a negative value. I know that this value right here is also going to be negative, and we're going to multiply them together. And when we multiply them together, this is going to create a positive value. So looking at the sign for delta H, it's negative. And so here, we don't really need to multiply or do anything to it. We just carry it down. And so once again, we get another scenario in which we have conflicting signs. Okay. And so this is telling us that when we have conflicting signs, the this is telling us that the Gibbs free energy, it's going to be not spontaneous at all temperatures. It doesn't mean that delta G will never be spontaneous, but perhaps there is a specific temperature that will allow it to be spontaneous if we have these conflicting signs. And so let's go ahead and look. We know that we cannot fix enthalpy and we can't fix entropy. That's something that's intrinsic to that chemical reaction. The only thing that we can change is temperature. And so if I wanted to make this reaction spontaneous, I want a higher negative value. So if I want this enthalpy to, if I want the sign or the value of enthalpy to dominate, then this value must be a lot less. Does that make sense? So this positive value must be smaller than the negative value. And the only way to make this positive value smaller is if the temperature is much smaller, right? So if the minus T is a small number, the value of the product is going to give us a small number. And we're going to hope that that small positive number is going to be small enough so that the negative sign of enthalpy will dominate at the very end. So it's going to be enthalpically driven. So here in this case, delta G is non-spontaneous at all temperatures. However, delta G is spontaneous only when temperature is low. Okay. So when the temperature is low, you get a small T delta S term. Okay. All right. So looking at what we've done in these four boxes, it looks like if just looking at the trends, notice that you have these conflicting results when the sign of your enthalpy and entropy are the same. So plus and plus would give us the conflicting result. Here we have minus, minus, and a conflicting result. Oh no, I didn't do it fast enough. So minus, conflicting result, and minus, right? So notice that the signs for enthalpy and entropy are the same, giving us conflicting results. And whenever we have conflicting results, we have to think about the condition for temperature that would allow the Gibbs free energy to be negative, producing a spontaneous reaction. All right, so what we're going to do is we're going to apply this to a couple problems, and then we're going to learn how to calculate the Gibbs free energy quantitatively instead of this qualitative assessment. And so here, will the reaction be spontaneous in the forward direction if delta H is 35.0 kilojoules, and the change in entropy is going to be 99.2 joules per Kelvin. Okay, so this is just like some made-up reaction. So notice that temperature is not given. So whenever temperature is not given, then you can't really calculate, you can't really determine the sign for the Gibbs free energy quantitatively. You'll have to do this qualitative assessment, this exercise that we did here. And so we know that delta G is equal to delta H minus T delta S. And so if delta H is 35 kilojoules, I don't really care about the number. I actually only care about the sign. So notice that it's a positive value. It's positive 35. And so this is going to be a positive value. Here, I don't really care about the value, but the only thing I care about is that it was positive to begin with. And so we have a positive sign. And so since we have a positive sign, excuse me. And so since we have a positive sign on both enthalpy and entropy, those are going to give us conflicting results, as seen in the problem above. Okay. And so here in this case, we have to figure out when this reaction would be spontaneous, or what temperature this reaction would be spontaneous. And so if we just kind of go through the process very quickly, so this is negative. This can be a negative value times this by a negative value. I'm sorry, negative times a positive, that's going to give us a negative value. Okay. And so if we're trying to get a negative delta G, okay, that means this negative sign has to dominate. And the only way that negative sign is, the only way that we can increase the value of that negative number is if we increase the temperature. And so here we will say that this reaction, AB to produce CD, is only spontaneous at high temperatures. And we don't really know the temperature at this point because, well, actually, we can figure it out by using these two values that's given to us. No, I'm going to leave that for a future lecture. And so for now, you guys, quote unquote, don't know how to determine this temperature that will give you this spontaneity, that will determine when this reaction will be spontaneous. The only thing that you do know is that the temperature must be very high. So here, if you have a very high temperature, this term is going to be a lot larger, ensuring that delta G is going to be negative. All right, so for the next example, will the reaction be spontaneous in the forward direction if delta H is negative 55 and delta S is 99.2? And so once again, there's no temperature that was given to us. Therefore, we need to qualitatively assess the spontaneity of this reaction by simply looking at the signs of enthalpy and entropy. So here we have delta G is equal to delta H minus T delta S. And so I don't really care about this value. All I care is the fact that it's negative. So I know that this term is always going to be negative. And according to my value for entropy, it's going to be positive. So I don't care about the value. And so here, if I multiply the T and the S term, the signs for the T, signs for the S, negative times positive is negative. If I add that with another negative value, which is coming from enthalpy, overall, delta G is going to be negative. And so since I'm getting negative values, then I can say yes, this reaction is spontaneous at all temperatures. Okay. So there was no like conflicting signs that will limit when the reaction will be spontaneous at certain temperatures. Okay. All right, so hopefully you guys got a better understanding of the Gibbs free energy. You guys understood when it's spontaneous, non-spontaneous, at equilibrium, and you guys hopefully understood how to qualitatively assess the spontaneity of a chemical reaction given just the values of enthalpy and entropy. In the next lecture video, we are going to take it to the next step, and we're going to quantify the Gibbs free energy. All right, see you guys in the next video.